Today, we're diving into something that's, well, it's kind of mind-blowing. It's a paradox at the very heart of all the tech we use every day. The absolutely insane cost of making things that are impossibly small.
Okay, let's just jump right in. Get ready for this, because it's a wild contrast. The chip inside your phone, maybe it costs $50. But the factory, the place that actually made that chip, we're talking somewhere in the neighborhood of $20 billion. That's billion, with a B. That's more than the entire infrastructure of a lot of small countries.
So yeah, that's the big mystery we're unpacking today. The main ingredient for these chips is silicon. And where does silicon come from? Sand. You know, the stuff that's literally everywhere? It's the second most common element on the planet. So how on earth did we take something that common and turn it into one of the most expensive and complex things humanity has ever created?
To get to the bottom of that, we first have to wrap our heads around what we're actually paying for when we buy a chip. And trust me, it's not what you think.
So here's the absolute key. The cost has almost nothing to do with the silicon itself. The real cost, it's in being able to control that silicon perfectly, billions upon billions of times on every single slice of it.
And this quote, man, it just nails it. This is the big idea you got to get your head around. We're not just carving tiny things into sand. We are fundamentally manipulating the building blocks of reality. This isn't your grandfather's factory floor. This is applied physics taken to its absolute limit.
So just how extreme are we talking here? What does atomic precision even mean in practice? Well, the tiny little switches that are the brains of everything, we call them transistors, are now being built at a scale of just 3 nanometers. Now, to give you some perspective on how ridiculously small that is, a single strand of your hair is about 75,000 nanometers wide. We are operating in a world that is almost impossible to imagine. You see, when you're working at this scale, the world as we know it, it just kind of falls apart. The normal rules don't apply. A single speck of dust isn't just a speck. It's like a meteor hitting your city. It can destroy an entire chip. A tiny little flicker in the temperature can ruin a whole batch of them. Heck, even one single atom in the wrong spot can change everything. Perfection isn't the goal here. It's the absolute bare minimum starting point. So, what do? How do you fight a battle where the enemy is physics itself? Well, you build a weapon. A very, very expensive weapon designed to fight it.
We call it a fab, a semiconductor fabrication plant. But honestly, that word doesn't do it justice. A fab isn't like any other factory you've ever seen. It's a gigantic, perfectly sealed machine built for one purpose: to create an environment that is cleaner, more stable, and more controlled than pretty much anywhere else in the known universe. And that is why it costs up to $20 billion. That's the price tag for creating this tiny bubble of perfection, where for a little while you can hold the chaotic laws of physics at bay. But let's go even deeper. Inside that $20 billion fortress, you've got all this specialized gear. And just one of those tools, a single machine using extreme ultraviolet light to print these circuits, costs over $150 million. For one machine.
So what happens when the price of admission is that high? Well, you get a very, very exclusive club. Right now, there are only a handful of companies on the entire planet. We're talking TSMC, Samsung, and Intel that can even afford to play this game. And that concentrates an unbelievable amount of technological and economic power into very few hands. But you know, it's not just about the money and the machines. There's another cost, a human cost, that's maybe even trickier to solve.
Here's a problem that every single chip company faces. You can have a brilliant engineer design a circuit. It looks perfect on paper, works flawlessly in the computer simulation, it follows every known law of physics. But then you actually make it in real silicon, and it just fails. For reasons no one could have possibly predicted.
And this right here, this is what people in the industry call the experience gap. It's why it's so hard for these companies to find new designers. It's not about being smart, everyone's smart. It's about having this deep, hands-on experience. It's about developing an intuition, a sixth sense for how silicon actually behaves in the real world, a sense you can only get by spending a decade watching your designs fail over and over and learning from it.
And just when you think it couldn't get any harder or more expensive, along comes AI, and it just throws gasoline on the entire fire.
The thing with AI is it's just so demanding. It needs to do a million calculations all at the same time. That's parallelism. It needs to access huge amounts of data like right now. That's bandwidth. And it has to do all of this without using a crazy amount of power. So what does that mean?
It means bigger chips, way more complex designs, and even less room for error, all of which sends the costs skyrocketing even higher.
All of this leads to a pretty obvious question, right? When the costs are this insane, when the physics is this difficult, why bother? Why keep going with this relentless, incredibly expensive chase to make things smaller and smaller?
The answer? Well, it's incredibly simple and incredibly stark. Because if we stop, everything else stops. Progress in almost every field you can think of, from AI and medicine to creating clean energy, it all just grinds to a halt. We're not just chasing smaller transistors. We're chasing the future.
So the next time you pick up your phone or use your computer, just think about what's really baked into that chip. The real price of that progress is measured in years of failed attempts, thousands of painful engineering choices, and billions of dollars spent long before a single useful product ever saw the light of day.
Look, this stuff isn't magic, it's precision, and it's been earned the hardest way you can possibly imagine. So it makes you wonder, if this is the high price we have to pay to keep moving forward, what's the even higher cost of just standing still?